So it's my pleasure to just briefly introduce the four presenters. Dr. Neal Allen, Associate Professor and Department Chair of Political Science, whose talk is titled Transactional Politics of Public Art, White Supremacy Never Dies. Dr. Nils Hakansson, Associate Professor of Biomedical Engineering, whose presentation is titled Biomechanics, Quantifying the Art of Movement. Dr. Ehsan Salari, Assistant Professor of Industrial and Manufacturing Engineering, whose presentation is titled Optimizing Radiation Therapy for Cancer Patients. And Dr. Aleksander Sternfeld-Dunn, Director of the School of Music and Associate Professor of Music Composition and Technology. His presentation is titled The Art of Failure. Each one will present after the other, and at the end there'll be time for questions, and then hopefully you'll join us for a reception. All right, thank you so much.
Okay, thank you so much. So what I want to talk about is the decision-making process by which portraits of former senators are hung in the U.S. Capitol, in this case near the Senate chamber, how that decision is made and what that tells us about race relations in America and also about the permanence of ideas, either good ideas or bad ideas. So this story is about three senators. James Ehsan, Democrat from Mississippi in the mid-20th century, and on the far left, Margaret Trace Smith in the middle, who is a Republican defender of free speech and civil rights from Maine in the mid-20th century, and on the right is Blanche Bruce, who was one of the two African Americans appointed to the Senate from Mississippi in Reconstruction. That's Chris Dodd. He saw that there were almost all white guys portrayed in the Capitol. He wanted to diversify things. He figured he would look for more people of color and women. And so he decided that it would be a good time in the early 2000s to put up to get a portrait made of Blanche Bruce. Bruce was not the first African American senator in America, but he was the only one for almost a century to have served a full term. The first was a man named Hiram Revels, also from Mississippi, whose portrait is in the Capitol in a different place. But both Revels and Bruce would not seek reappointment. Remember, this is at a time in the 1870s when we didn't directly elect senators. Neither one of them would seek reappointment because by that point it was impossible because the white supremacists who happened to be in the Democratic Party in the Mississippi at the time had reasserted their power and were controlling state politics both through legitimate means and through illegitimate means with their paramilitary arm, the Ku Klux Klan. So when Chris Dodd decided about 140 years later that he wanted to honor Blanche Bruce, he also ran into a roadblock, and that was in the form of a man named Trent Lott. Trent Lott was the ranking member of the Rules Committee, which is who handles administration matters in the Senate. Lott, you might remember from his service in the Senate because he was the Republican leader, but right about a year after the period I'm talking about, he ceased to be the Republican leader in the Senate, and that was because of saying really nice things about a man named Strom Thurmond, in particular saying that if Thurmond himself had won the presidential election in 1948, I think the quote was, then we wouldn't have had all these problems over all these years. So Lott's proposed deal to remove his block of Blanche Bruce being honored was to honor one of his mentors, James Ehsan. Ehsan served in the Senate from 42 to 1978, rose to be chair of the Judiciary Committee for over 2 decades, and systematically did everything he could to block civil rights legislation, including just refusing to call on members of the Senate who wanted to talk about that at meetings. And so Lott said, if you want your Blanche Bruce, you got to take my Jim Ehsan. So we got transactional politics. In a lot of ways, making a deal with the devil, but there's still a deal to be had. And so that gets us better representation in the Senate chambers. And so if you want to get a man who was a member of the Senate, risk his life to be a member of the Senate, spent the rest of his career after he was basically blocked from advancement, attempting to get patronage appointments to pay the bills for the rest of his life. If you want to get this guy, then you have to get the guy on the left, James Eastland, and Margaret Chase Smith was kind of thrown in as a woman to be named later. But Chris Dodd, being a practiced politician and actually a son of a senator, said, I got the better deal because I got 2, and Trent Lott only got 1. So what does this tell us about how politics work and how our culture works? Well, ideas never die. And those can be really wonderful, important ideas like racial justice or gender justice, but also it can be horrible, evil, awful ideas like white supremacy. So, and how should we think through that? Because, as I wait for 20 seconds, white supremacy never dies. So what are we going to do about that? Or how do we think through that? Because it's an idea that never dies, but it can be in some ways beaten into submission and removed from the core of national power. And that's happened twice. Once in Reconstruction, and prior to that the Civil War, which took more than 500,000 people died just to get to a brief period of black empowerment, or in the civil rights movement of the mid-20th century, which brought us legislation like the Civil Rights Act. This was the Selma Montgomery March in 1965 that brought us the Voting Rights Act. But still, if you go to the U.S. Capitol, you want to go into the Senate chamber, if you walk the right way, you'll see another reminder that white supremacy never dies. And if we needed another reminder of that in our current politics, we could focus on the events in 2017, in the summer of 2017, in Charlottesville, Virginia. Here, as at the University of Virginia, just down the hill from the rotunda, the Jefferson statue is right up above on the top right. And so we can see that white supremacy never dies. But white supremacy is not the only idea that never dies in our culture. You know what else never dies? Democracy never dies, as shown by the massive turnout of voters in the midterm elections in 2018 that brought in a whole new class of freshman House members or senators, including many women of color, many women who are not heterosexual, and also a group of men that supported civil rights. Also, what never dies? Music never dies. And also, to all you northern elitists out there that don't know who the guy is on the right, that's Dwayne Allman of the Allman Brothers Band. And finally, what else doesn't die? Art never dies. So this is titled Department Store, Birmingham, Alabama, photographed by Gordon Parks, 1956, in the permanent collection of this museum. Thank you.
So I noticed that I didn't put my name on the front slide here. So if it goes well, I'm Nils Hakansson. And if it doesn't, it's Ehsan Salari. Okay. So when I bring in students to the lab, we actually do a lot of lab tours, and so one of the questions I have for them is, what is biomechanics? And I like to let them know that it's not the person or the people who fix your car, along with biological systems, but instead it is the biological systems on the right there, which I like the old art, and Newton's laws. So looking at inertia, the first law of body in motion stays in motion, force equals change in momentum, and then action-reaction. Relatively new is the field of biomechanics, although yet you could argue it isn't. And it's a very diverse field. So it covers a lot of topics, including animal and human locomotion, biotriviology, which I had to look up, which is basically friction, and it's friction in the joints. And I like the image there from Da Vinci, where he was doing some early experiments with friction. And then human biomechanics, I like to share with the idea of mechanical systems, but as it relates to the body. So forces, moments, and how those are all incorporated in how we move and achieve tasks. And my particular interest, and this slide I'm afraid got shifted, there should be an arch with a question mark, is how do we go from a thought to an actual movement, and a skilled movement at that. So we have a picture from Muybridge of an individual walking and running. And for those of you who are not sort of in the biology world, initially we come up with an idea for movement in the brain, and then we send signals down the spinal cord and to the peripheral nervous system, and then that interacts with our muscles and the bones to then get a skilled movement. And this is also from a photographer named Muybridge, and he took a lot of pictures of women, and this was the only ones I could find in which they were wearing clothing. So thought maybe it'd be more appropriate this way. But that's a general flow chart of how we move. Now, as engineers, we look at it from another perspective. And so we have initially some neural control, sort of the idea of motion, that will then send a signal to the the muscle tendon, the muscle system, so that we can then activate the muscles. Those will generate forces, which then are applied to the bones. And then with that, we get some moments, and basically our motion is all based on a torque or a moment. And then from that, in the modeling approach, we can look at accelerations. So F equals ma. And then we do some integrations, and we can get positions, and some velocities. And then we end up with a movement. And there's a feedback loop that will then go back, and we change the control. So if we overreach or underreach, we know to make some adjustments, and we have that built into our nervous system. But the computer models, we do this in another approach. So we might have our initial input, or the brain signal, a simplified one, is shown here as a square wave, and this was designed for a pedaling experiment. So we'd have at some point, as we pedal the bike, we turn on the muscle, and then at some point we turn off the muscle. And then we have an amount of amplitude will tell us how much we activate the muscle. And then that would go through this process to activate the muscle from the nerve, which we release calcium to then have the muscle generate force. And I have a little math here because I'm an engineer. But the idea is there's a time delay. And so you get the electrical signal, and then you get a movement, and then the electrical signal goes to the muscle, and the amount of force that's generated is a function of the length of the muscle, the velocity of the muscle, and the amount of activation of that muscle. And that's represented by that surface there. So depending on different conditions, you'll generate different forces. And then those forces are transmitted to the body through the muscle origins, or where the muscle starts and where it ends, and then the moment arm that will cross the joint, so we can generate the torque, and then how the joints will actually move. And then coming back to Newton, we need to know some of the movement characteristics, so we can program this into the computer in terms of, here we have the thigh, the lower leg, the foot, and then a crank for a bicycle situation. So we need to understand the masses, the accelerations, and then we can get an idea of the forces. And then from our model, we would get some we'd have the output, which is the blue dark line, or the experimental data, which we might collect from people. And we want to see how well does our model represent what we actually measure and what people really do. And we can do that, and we calculate what's called a cost, or through a cost function. And if we don't get very good agreement, we can go through this iterative process. So initially, we make a guess. Is this what we want to put into the system? We put it into the system. We compare what we measure from real people to what our model will generate. If it replicates well, we're done. If not, we go through the cycle again. So here we actually have a graduate student who wasn't doing his job and was taking a nap on the floor. Well, actually, he was doing some rolling for us. So our current use of this model is on how people roll. So the idea is that we want to learn how people roll in a natural condition, and then we can compare it to people who might not be able to roll. So we're designing a computer model of this motion so we can design a mattress to help people roll who can't presently. And that's it.
Hi everyone, thank you for the invitation. So what I would like to talk about is the role of mathematics and engineering tools in designing radiation treatment plans for cancer patients. So according to the American Cancer Society, this year there will be 1.7 million new cancer cases in the United States. Cancer is the second leading cause of death, and in Kansas there will be more than 15,000 cases. There are a range of treatment modalities for cancer, including surgery, chemo, radiation, and usually cancer patients receive a combination of those, but radiation is commonly used and more than 50% of all patients benefit from radiation therapy. In radiation therapy, high energy radiation beams are used to eradicate cancer cells, and as they pass through the patient's anatomy, they basically kill cells, both healthy and cancerous cells, by damaging their DNA molecule. So the goal of radiation therapy is to essentially deliver a prescribed dose of radiation to the target region while sparing the surrounding healthy tissue to the largest extent possible. And to achieve that, we usually use a combination of beams situated around the patient in order to spare the healthy tissue. Intensity modulated radiation therapy, or IMRT in short, is a common radiation delivery mode that uses a linear accelerator to deliver radiation, and the head of this accelerator is equipped with a multi-leaf collimator system, as you can see on the right, to modulate the aperture shapes. Now, in order to design an IMRT plan for a patient, we need to figure out how many beam angles we want to use, in what orientation, what should be the intensity profile of each of those beams, the number of apertures from each beam angle, the exposure time, and so on. When you think about it, this is really an optimization problem we are solving. We're trying to find the optimal deliverable plan for an individual patient, such that we minimize normal tissue exposure to those, while ensuring that we're delivering a prescribed dose to the tumor region. This can be modeled as an optimization, a mathematical optimization problem, and that's actually what I do as a major part of my research, basically coming up with these optimization models and solution methods to solve them efficiently. And these are typically very difficult problems to solve because they're very large scale and nonlinear. Now, motion is a major concern in treatment of lung and abdominal cancers because, particularly due to respiration, we have large tumor displacements as well as deformation in the nearby organs. So there are different ways to essentially manage motion during radiation delivery. Traditionally, these motion reduction techniques have been used, for instance, using abdominal compression to limit the range of motion and also to control the respiration behavior of the patient. However, this causes inconvenience to the patient. Another approach is to include this motion within the treatment so that rather than treating the target itself, we irradiate an expanded version of the target so that we ensure that the target and its range would be within the radiation beam. But that would cause essentially exposure of normal tissue. Now, a new development in the field is using these hybrid MR-LINAC systems that essentially integrate an MRI scanner within the LINAC in order to get a visualization of the anatomy as we treat the patient. This basically brings sight to radiation. Now, currently, respiratory gated treatments are used where this real-time visualization is used to track the tumor, and every time that the target is out of a boundary, basically we can shut the beam off, and when it is back in the specified region, we can turn it on again. Now, what we are working on currently is using a real-time motion adaptation approach to MR-LINACs, where similar to self-driving cars, we want to analyze these real-time images that we acquire from MRI and basically use those to plan the path forward. To do so, the first step is to be able to track motion on these images. So what we do is we keep track of a region of interest and see how much displacement we have in that region, and that would allow us to generate a motion signal. And that's basically what we use to track a patient's motion. Now, if we want to adapt to motion, we have to be a few steps ahead of it. So in order to do that, we need to accurately predict motion in real time. So what we do is we build basically mathematical models to accurately predict motion, and in particular, the motion signal we generate from the images. Also, we need to be able to keep track of the dose we have delivered so far. So we use image processing tools to basically see how much dose has been accumulated in the anatomy, and by doing that, we are basically able to monitor the progression of radiation delivery. Using these dose accumulation and motion prediction, then we optimize dynamically the radiation plan for the remainder of the treatment in real time, so that we are basically able to correct for any dose discrepancy and also to adapt to changes in real time. Now, the benefit of this is twofold. One, we would be able to improve the accuracy of radiation delivery, but also we would be able to shorten the treatment time because the treatment is continuous. We don't turn the beam off, similar to gating. And the impact could be potentially high because lung cancer cases are the second, basically, deadly cancer disease. This is a joint effort. Just wanted to acknowledge my collaborators. This is a joint effort with Mass General Hospital, Washington University in St. Louis. And the work has been funded in part by the National Science Foundation. Thank you.
Hello. We're going to talk about failure. You'll know it well. So in my professional life, I am a man who wears numerous hats: teacher, administrator, composer, advocate. And while on the face of these things, these hats sometimes look very different, there is typically one thread that connects them all. And that thread is one that we've all experienced, and it is known as failure. My first significant experience with failure as an artist happened my freshman year of college. I walked into my composition teacher's office for the first time, sat down at the piano and began to play through an orchestra work I had been writing. After about 5 minutes into the lesson, he looked at me and he said, "You know, Alex, this isn't very good." While I found this news disheartening at first, I was equally inspired to find out what was going wrong. You see, as artists, we're programmed to experience failure on a daily basis and to persevere through it. We call this the creative process. What I have found interesting in recent years, amongst other artists, is while we are comfortable facing failures in our artistic lives, we are not as comfortable in addressing the failures that our current arts institutions are facing. As we face a declining audience base, a less educated arts audience, declining public funding, the reaction of many institutions is not to change, but to dig our heels into tradition even farther. An important piece of data I'd like us to consider is that according to the National Endowment of the Arts, over the past 20 years, 40% of arts organizations have perished. 40%. Some good news. They're being replaced even faster, though. For every arts organization that survived between 1990 and 2010, 2.6 more were born. But I'd like to go back to that 40% failure rate. It was astonishing to me. This number and the sometimes unwavering stubbornness of organizations has led me to a change in my own personal research, moving from being a composer to actually looking at how organizations deal with failure, and more importantly, how arts organizations begin to change. To start with, I would like to explain a concept designed by faculty at the Kansas Leadership Center based on research done by two Harvard government professors, Professor Marty Linsky and Ron Heifetz. It's called your personal bandwidth. The top horizontal line represents all the world's people. The bottom line represents all the world's situations. The space between the two parallel solid lines is you. Everything about you, your values, your experiences, preferences, triggers, etc. It is the space between these two parallel lines in the middle that represent the range of situations we are suited to intervene in. As challenges begin to rear their ugly heads, our typical instinct is to engage in the behavior that will keep us within those two lines. We all have a history, as do most arts organizations, that suggests that we can solve these challenges using our typical behaviors. But, as we reflect on those failed arts organizations, if we do so, we will join the 40%. So today I'd like to propose two types of failure. One is the failure that happens when we stay between those two lines, and the second is the failure that comes when we are willing to experiment beyond our comfort zones. For the purposes of today's talk, we're going to focus on that second type of failure. You see, when you choose to try something that is outside of the realm of your standard behavior patterns, you are choosing to engage in experimentation. As any good scientist will tell you, and there's some in this room, experiments are never failures. They're simply ways to collect data to test our hypotheses. So then the question becomes, what keeps us between those two lines? Well, it reminds me of the great 1997 movie Wayne's World. We fear change. However, Garth is unfortunately not entirely accurate. My belief is that we don't actually fear change at all. If I gave you $5 million, that would probably change your life, and you're probably not scared of that. What we're scared of is loss, which brings me to Century 2. When you hear the rhetoric surrounding Century 2, the most common speeches you will hear is, this is a historic part of Wichita. This is our identity. What I've never heard spoken is, this space is amazing to perform in, it's totally appropriate for the arts organizations that exist here. Instead, the arguments are always about loss, and specifically a loss of identity. So what do we lose if we succeed? This may seem like an odd question. Isn't the point of success to somehow win? Well, anybody who has won can tell you that to win, you have to lose. When we are in the midst of adaptive work, we can sometimes find ourselves banging our head against the wall, trying to understand why people are unwilling to make change. The answer is typically because if we are able to make progress on something, it will mean loss as well, which brings me back to Wichita State. The mantra you will hear most often spoken on this campus is the need for enrollment growth. We know that if we can grow enrollment, that growth will help solve numerous issues. It'll bring more tuition dollars and fee to help our funding woes. It will create a more vibrant and a diverse campus, and it will raise the national visibility of our university. Yet why are we stuck at 16,000 students? Perhaps, and this is just a thesis, we're self-sabotaging ourselves. Because what we haven't yet discussed is what we will lose with the growing enrollment. Larger class sizes mean more students to interact with. It means more papers to grade. It means less time to research, more pressure on a failing infrastructure. For some, it might mean less time to do all the things that we love to do and more time advising. That's a lot of loss if we were to succeed. Yet we recognize the need that for us to avoid being a part of that 40%, we must adapt, we must experiment, and speak to the loss that comes naturally with both progress and failure. To do that, we must expand our bandwidth by understanding ourselves and our organizations on a deep level, who we are and who we are not, our skills, our vulnerabilities, and the ways others see and experience us. Finally, we need to be willing to take the first step to the edge of our incompetence and see what experimentation might look like. Thank you.